Hello everyone, welcome to the 30th ACM International Conference on Multimedia. My name is Xiaodong Chen. I'm a PhD student at the University of Science and Technology of China. I will introduce our work, Maple Masked Pseudo-Labeling autoencoder for semi-supervised point cloud action recognition. This paper is co-authored by Wu Liu, Xingchen Liu, and Tao Mei from Jingdong Explore Academy, Yongdong Zhang from University of Science and Technology of China, Jungong Han from Observatory University. This is our outline. We will start from the introduction of semi-supervised point cloud action recognition with the motivation of our paper. After that, I will talk about our Maple framework, experiment results, and some important application studies. Point cloud videos compared with RGB videos contain richer visual and geometric information for action recognition. In detail, point cloud has more strict information, which gives it a huge advantage over RGB videos in the field of object detection, segmentation, and so on. However, due to noises, ambiguity, and irregular data format of point clouds, how to learn discriminative features and model the spatial temporal patterns from point clouds is a great challenge. Nevertheless, due to a huge potential of point cloud videos, more and more researchers from academia and the industry recently have focused on the point cloud action recognition task. This task can be treated as a 3D video classification problem. It's a hot topic of video understanding in computer vision. It has wide potential applications in industry, manufacturing, robotics, and so on. Based on the characteristics of previous methods, three main types of point cloud action recognition have been distinguished. The first one is mainly based on voxels obtained from point clouds. 3D dynamic voxel, 3DV for short, bring the voxelization of point clouds into point cloud action recognition via temporal rank polling. This type of method effectively solves the problem of irregular data format, but has the weakness of low computational efficiency. The second type of method is directly performance of the original point cloud with PointNet-based models. For example, MeteorNet further constructed the conception of spatial temporal neighborhoods based on the point cloud and determines neighborhoods with direct polling or chain flow grouping. This type of method has high computation efficiency, but limited by the weak spatial temporal modeling capabilities. Last type adopts the data-hungry transformer-based model. Representative works in recent years including P4 transformer and PST2. They modeled the action and appearance information of the whole video while effectively discarding the requirement of point tracking used in MeteorNet and the complex calculation of voxelization. In summary, on one side, these mainstream approaches are limited by the trade-off of modeling capability and computation complexity. On the other side, they usually rely on the labeled data, insufficiently leveraging unlabeled data. Therefore, this paper focuses on the task of semi-supervised point cloud action recognition, which aims to reduce the reliance on manual labels using a more efficient framework. To overcome the trade-off of modeling capability and computation complexity, we designed an efficient backbone named Decoupled Spatial Temporal Transformer, transformer for short. They capture multi-scale temporal information, short-term and long-term, for efficient modeling, and decouple spatial temporal structures to reduce the computational complexity. Further, to leverage large-scale unlabeled data, we propose a semi-supervised learning framework named Masked Pseudo-Labeling autoencoder, Maple for short. It masks and restricted the short-term features for self-supervised training and implicitly instruct them with the pseudo-label for stable convergence. We will introduce the design of our transformer backbone and maple framework in detail in the next slide. First, we will introduce our transformer in detail, which consists of the following four modules. Data preparation is the first module of our transformer. For the import point cloud video, we construct some local area, for example, A, B, C in this slide, on adjacent frameworks as what points for the convolution do. The calculation of the local area is based on the classical farthest point sampling, FPS for short. After that, special structure is planned to structure the short-term feature MI from the local area, and the temporal aggregator aggregates the long-term global ZI from the short-term feature. To achieve the lightweight network design, the special transformer is designed with only 4 self-attention blocks, and the temporal decoder is designed with only 3 self-attention blocks. Following the temporal aggregator module is the prediction hand. It rules it to project the global feature Vi into the label space and generate the corresponding pseudo-label for classification. This design not only provides efficient modeling capabilities but also greatly reduces computation complexity. Moreover, we adopt our transform as the backbone of our semi-supervised framework Maple for semi-supervised point cloud action recognition. As shown in the left part of this slide, we adopt our transform backbone and the cross-entropy loss for supervised training with labeled point cloud videos. Besides, the right part shows the complete training process of our Maple with unlabeled point cloud videos. Similar to the reconstruction process of autoEncoder, the special instructor encodes the point cloud video as a short-term local embedding feature GI. The temporal encoder of our Maple projects the visible subset of embedding feature GI into latent space delay. The temporal decoder is responsible for restriction from the latent representation Zi and the learnable mask token M. However, different from classical autoencoder, our Maple implicitly restricts the original single through the pseudo-label generated from the classical hand rather than reconstructing the original single itself. Compared to restructuring the original feature, reconstructing the pseudo-label not only improves the performance of classification but also makes the training stage more stable. We compare these two strategies in detail in the ablation studies. Our experiments are performed on 3 main human action recognition datasets: MSR Action 3D, NTU RGBD 60, and NTU RGBD 120. For our semi-supervised point cloud action recognition task, about 5%, 10%, 20%, 30%, and 40% of training videos of each action are selected for the labeled dataset DL. In detail, as shown in the right table, we divide each dataset into labeled training dataset DL, unlabeled training dataset DU, and the testing dataset DT. Based on the experimental setting on the previous slide, we have conducted detailed experimental comparison, and some experimental results are shown here. To demonstrate the validity of our special temporal backbone, left side of this slide shows the action recognition performance between our transformer and the P4 transformer model with the supervised only setting on NTU RGBD 120 data size. We observe that our transformer has less annotation dependence and better classification performance in supervised-only setting, especially on the NTU RGBD 120 20% labeled state setting. Our transformer model generally obtains a greater than 9% increase in the action recognition accuracy. Right side of this slide evaluates our Maple method by comparing it with leading semi-supervised methods. For example, pseudo-label, VAT, and ENT-min. For semi-supervised point cloud action recognition on the MSR Action 3D dataset. From the semi-supervised readout of each semi-supervised method, we can find that our Maple method is effective for semi-supervised learning and slightly outperforms the previous method's performance under most settings. We also observe that our Maple method can be combined with other leading semi-supervised methods and obtain significant performance increase on each setting, especially on the 7.5% labeled MSR Action 3D setting. It brings significant 8.08% accuracy improvement in the action recognition performance. In addition to the basic experiment results on mainstream dataset, we additionally analyze the influence of the masking ratio and the depth of the temporal decoder. The left feature shows the accuracy of classification on the NTU RGBD 65% labeled datasets with different masking ratios. The high masking ratio, 75% of restructuring achieves a peak of classification performance. Policies that most frames of the action sequence are redundant and we can reject the complete action sequence from the small residual part of the sequence. The influence of temporal decoder depth is shown in the right figure. It proves that the depth of the temporal decoder doesn't have a large impact on the performance of the final classification. Therefore, a decoder of shallow depth is sufficient to reconstruct the complex sequence. Finally, let's conclude this presentation with a summary of our paper. This paper is one of the first attempts towards semi-supervised point cloud action recognition. We designed a decoupling spatial temporal transformer named DESTformer. With this DESTformer, we propose a mask pseudo-labeling autoencoder framework for semi-supervised point cloud action recognition.